In this video, we will discuss about a type of weak force, that is van der Waals forces. Before we begin, let me ask you a question. Is a force of attraction between non-polar molecules? We know there are forces of attraction between polar molecules, means there will be electrostatic force of attraction between the negative charge and positive charge. But here the question is there a force of attraction between non-polar molecules? Will two non-polar molecules attract or repel each other? The answer is yes. There is forces of attraction between non-polar molecules. And these forces are called intermolecular forces or cohesive forces, also known by the name van der Waals forces. And these include attractions between atoms, molecules, and even attraction between surfaces. Now, how do you define these van der Waals forces? It's the sum of attractive and repulsive forces between molecules other than those due to covalent bonds. It means that van der Waals forces are not covalent bonds. It is something different from covalent bonds. And it is just the attractive or repulsive forces between molecules other than those due to covalent bonds. And they differ from normal covalent bonds and ionic bonds in that they are caused by correlations in the fluctuating polarizations of nearby particles. And as we know, covalent bonds are strong bonds, but these van der Waals forces are very weak in nature. They are weak forces. Now these forces, that is van der Waals forces, which is also known by the name intermolecular forces or cohesive forces, play a fundamental role in different fields like supramolecular chemistry, structural biology, polymer science, nanotechnology, surface science, and condensed matter physics. So you can see these forces play a great role in fields as diverse as supramolecular chemistry to surface science. And they define the chemical characteristics of many organic compounds. They also define the solubility of organic substances in polar and non-polar media. Now, what this originate from different types of interactions. The first type of interaction is dipole-dipole interactions, and these are also known by the name keystone forces. It is an interaction between two dipoles. Now, the second type of interaction is ion-dipole interactions, which means there is the interactions between an ion and a dipole. The third type is dipole-induced dipole interactions, means the interaction between one dipole and an induced dipole. This is also known by the name Debye forces. And lastly, you have induced dipole interactions, which are also known by the name London forces. So the van der Waals forces originate from these four types of interactions. We will see one. First, we will see about the dipole-dipole interactions, which are also known by the name keystone forces. These forces, means keystone forces, are van der Waals forces which originate due to electrical interaction between the dipoles. Means it is just an electrostatic interaction between two dipoles. As the name suggests, it is an interaction between one dipole and another dipole. And where do we find a dipole? In polar molecules. So this kind of forces is applicable for polar molecules which have permanent dipoles. For example, we have a molecule like HF, where we have already seen that fluorine is more electronegative than a hydrogen, therefore fluorine has a negative charge and the hydrogen has a positive charge. So this type of interaction leads to, these molecules are polar molecules which have permanent dipoles, and in this case the positive end of one HF molecule is attracted to the negative end of another HF molecule. Also, the positive ends of two molecules repel each other also. So, such kind of interactions, the sum total of all these interactions is what we call as keystone forces. So, please note, keystone forces exist in polar molecules which have permanent dipoles. Other examples of molecules which show keystone forces are HCl, NH3, sulfur dioxide, etc. Magnitude of these keystone forces or dipole-dipole interactions depends upon the dipole moment of the molecules because it is applicable to polar molecules and polar molecules have permanent dipoles. So greater the dipole moment of the molecules, greater will be the magnitude of keystone forces. Because of these attractive forces, these gases can be easily liquefied as well. Now the strength of keystone forces is weaker than a covalent bond because we already know covalent bonds are very strong bonds whereas keystone forces are very weak bond. If you compare the strength of keystone forces to that of a covalent bond, you can see that the keystone forces are 1% as strong as covalent bond. Means it is a very weak bond. And these keystone forces, also known as dipole-dipole interactions, are weaker than the other types of interactions, other types of van der Waals forces, that is ion-ion interaction and ion-dipole interactions. Now let's compare the melting point and boiling point of polar molecules with that of non-polar molecules. Which of these will have higher boiling point? Suppose suppose these two molecules have same shape and same molecular weight. We know that polar molecules, one example is HF molecule. Such molecules usually have high melting point and boiling point compared to non-polar molecules having same shape and same molecular weight. And this is because of the presence of keystone forces. And we know greater the polarity, higher will be the melting point and boiling point. Because there is an additional interaction between these molecules, that is a electrostatic force of attraction between the two dipoles. So greater the polarity, greater will be these attractive forces and therefore higher will be the boiling point and melting point. Now let's compare the dipole moments. We have two molecules here, water and ammonia. The question is, which of these has higher boiling point? Does water has a higher boiling point or is it ammonia which has a higher boiling point? The dipole moment values are given. For water, the dipole moment is 1.85 dB. For ammonia, it is 1.49 dB. So which of these molecules has higher boiling point? Now in the last slide, we have seen that greater the dipole moment, greater will be the melting and boiling point. So if you compare the dipole moments of the two molecules, you can see water has a higher dipole moment, which means water will have higher boiling point. So the dipole moment is a measure of polar nature of molecules. Higher dipole moment indicates higher polarity and molecules with higher dipole moments have higher melting point and boiling point. Now let's see the second type of interaction, which is the ion dipole interactions. Now these forces exist between an ion, a cation or an anion, and a polar molecule. Forces of attraction which exist between an ion and a polar molecule, that is ion and a dipole, is called ion dipole interactions. Like this. This is an ion. This is a permanent molecule with permanent dipole or a polar molecule. It has dipoles and there will be attractive forces and also repulsive forces acting between this ion and this polar molecules because of these charges. So this type of interaction is called ion dipole interactions. And the strength of such attractions or interactions depends on two factors. One is the charge and size of the ion. The second factor is the size and magnitude of dipole moment of the polar molecule, right? Magnitude of dipole moment of this polar molecule, and also charge and size of the ion are the two factors which determines the strength of this ion dipole interactions. We know that now if you compare the strength of interactions between a cation and a polar molecule and an anion and a polar molecule, which will be of greater strength. Means we have already said that the ion dipole interactions exist between an ion and a polar molecule. So this ion can be either a cation or an anion. So which of these interactions will be higher? Interaction between a cation and a polar molecule or an anion and a polar molecule? Which of these will be higher? Please note, the strength of interactions depends on what? The charge and size of the ion, right? So we have to look, we have to see which of these ions, that is whether a cation or an anion, has greater charge and greater size. As we know, cations is smaller in size, right? So the charge density on cation will be greater since it is having smaller size, which means the interactions between a cation and a polar molecule are more stronger than the interactions between an anion and a polar molecule. So in the case of ion dipole interactions, the strength of interaction will be greater between a cation and a polar molecule. Now let me ask you one question. Sodium chloride and potassium chloride. Both these are soluble in water, as you know. But these two molecules, that is sodium chloride and potassium chloride, are less soluble in CCl4. What is the reason? We know water is a polar molecule, whereas CCl4 is a non-polar molecule. So sodium chloride and potassium chloride are soluble in a polar solvent, but not soluble in a non-polar solvent like CCl4. What is the reason? This is because when sodium chloride and potassium chloride, molecules like sodium chloride and potassium chloride, are dissolved in water, the ions, that is sodium ions and chloride ions in the case of NaCl, or in the case of potassium chloride, K plus and Cl minus ions, are immediately surrounded by oppositely charged ends of water molecules, because sodium chloride is an ionic compound. It will exist as Na plus and Cl minus ions. So you have an ion there. Then if you dissolve it in water, water being a polar molecule will have dipoles in it. So the sodium ion will be immediately surrounded by oppositely charged ends of this water molecule. These represents water molecules. So this is sodium having a positive charge. This is water molecule which exists as a dipole, where this is oxygen. The red one is oxygen, and oxygen has a negative charge. The other two white spheres represent hydrogen atoms which have positive charge. So you can see the negative charge negatively charged end of water molecule comes closer to the positively charged sodium ion. So in this way, sodium ions are surrounded by oppositely charged ends of water molecule. Similarly, chloride ion will also be surrounded by the positively charged ends of water molecule. So in this way, both sodium ions and chloride ions are surrounded by oppositely charged ends of water molecules having large dipole moments. So what happens there is a type of ion dipole interaction, right? There occurs a ion dipole interaction between this sodium ions and this water molecules. So this means that the water molecules keep the ions apart. Means sodium ions and chloride ions will be separated by this sphere of water molecules. Since the ions interact with water, they become soluble. If there is greater interaction between the substance and the solvent, greater will be the solubility. So in this case, you can see the sodium ions and chloride ions interact much with water. Therefore, these ions or this substance becomes easily soluble in water, which means water is an excellent solvent for ionic compounds like sodium chloride and potassium chloride. But if you take CCl4, CCl4 is a non-polar liquid. It cannot participate in this type of ion dipole interactions with sodium chloride and potassium chloride, because since it is a non-polar molecule, this type of interaction or solvation will not occur in the case of CCl. So that is why sodium chloride and potassium chloride is soluble in water, but these are less soluble in CCl4. Now the third type of interaction is called ion-induced dipole interaction, which is also known by the name Debye forces. So as the name suggests, it is an interaction between a dipole, that is a polar molecule, and an induced dipole. That is, you have a molecule with permanent dipole, that is a polar molecule. If it comes closer to a non-polar molecule, there will be some kind of interaction. That is, this polar molecule can induce polarity in this non-polar molecule. Means this polar molecule, the positive charge, positive end of this polar molecule can attract the electron cloud of this non-polar molecule towards itself. Thereby, a dipole will be induced in this non-polar molecule. So this type of interaction is called a dipole-induced dipole interaction. This polar molecule induces polarity in this non-polar molecule, and we call it as this becomes an induced dipole. So the interaction between this polar molecule and this non-polar molecule is called Debye forces. And the polar molecule polarizes a non-polar molecule and induces dipolarity in the molecule. The induced dipole is then attracted to the polar molecule. So this kind of interaction is called Debye forces. The magnitude of Debye forces depends on again two factors. One is magnitude of dipole moment of the polar molecule, and of course the polarizability of this non-polar molecule. Means how easily this non-polar molecule can be polarized. So these are the two factors on which the Debye forces depends on. Debye forces also exist between an ion and an induced dipole. It is also called by the name ion-induced dipole interaction. Okay, so not only Debye forces exist not only between dipole-induced dipole, that is a polar molecule, and an induced dipole, but also between an ion and induced dipole, because ion, being a charged atom, can induce polarity in a non-polar molecule, making it an induced dipole. So then this induced dipole will be then attracted to this ion. So this type of interaction is called ion-induced dipole interactions. And the fourth type of interactions is called induced dipole interactions. These are also known by the name London forces or dispersive forces or even van der Waals forces. So these forces exist between non-polar atoms, that is atoms like inert gases like helium, argon, neon, etc. These are non-polar atoms. They also exist between non-polar molecules. Say for example, homoatomic molecules like hydrogen, nitrogen, oxygen, etc., which are non-polar molecules. Consider a non-polar molecule. This non-polar molecule has a positive center, that is the nucleus, and an electron cloud around it. Now this electron cloud moves around this positive center in a symmetrical manner. Now it is supposed that the symmetrical movement of this electron cloud becomes unsymmetrical for a fraction of a second. Right? Imagine that the symmetrical movement of this electron cloud becomes unsymmetrical for a fraction of a second. So what happens? The spherical nature of this electron cloud will be lost, and there will be an elongation of this electron cloud for a fraction of a second. So at that given instant, the positive charge may be concentrated in one region and the negative charge may be concentrated in another region, like this. Or we can say the non-polar molecule has become self-polarized momentarily. for a fraction of a second, the non-polar molecule become self-polarized. Now this polarized molecule can induce a dipole moment in another non-polar molecule. Right? When the self-polarized molecule comes closer to a non-polar molecule, it can induce dipolarity in this non-polar molecule as well. So this kind of interaction, or this kind of the attractive forces and repulsive forces which exist between these two dipoles is called induced dipole interactions. Because why is it called induced dipole interaction? Because the first molecule was self-polarized and the dipolarity was induced in this first molecule. And this first molecule induced polarity in the second non-polar molecule. So this is an induced dipole. The second one is also an induced dipole. Or you can say the first molecule is an instantaneous dipole because it was momentarily self-polarized. So it is an instantaneous dipole, induced dipole interaction. Or it is also simply known by the name induced dipole interaction. Now, since all molecules contain electrons, these type of forces, that is induced dipole interactions, also known by the name London forces or dispersive forces, exist in polar molecules as well. Because polar molecules also contain electrons and electron cloud. So this kind of self-polarization can occur in polar molecules as well. But in the case of non-polar molecules, the only forces or the only intermolecular forces that exist are the London forces. But in polar molecules, apart from London forces, we have already seen the other types of interactions that are possible. Now for a pair of adjacent molecules, the London forces is found to vary inversely as a sixth power of the distance between them. So in this formula, R represents the distance between the adjacent molecules and F represents the force of attraction or the force that exists or the London forces or the strength of this London forces. Okay, so F is inversely proportional to the sixth power of the distance between the molecules. Let's see the characteristic features of van der Waals forces are very weak than both covalent bonds and ionic bonds. Van der Waals forces are found to be minimum among gases but a little more in liquids, and van der Waals forces exist maximum in solids. The stronger the forces, higher will be the melting point and boiling point. Means greater the van der Waals force, greater will be the melting point and boiling point. Also, van der Waals forces are not affected by the presence of other atoms or molecules. So, if there are other atoms or molecules, or even in the absence of other atoms or molecules, this kind of forces exist. So, it is independent of the presence or absence of other types of atoms and molecules. Now, let's see what are the factors affecting the strength of London forces or van der Waals forces. The first factor is the atomic size and molecular size. So how does the atomic size affect London forces? You know, atoms with large size will have large electron clouds. So their electron clouds will be diffused and distorted, which means they can be easily polarized. So in such cases, the strength of the forces will be very high. So the London forces are stronger in big molecules. So as atomic size and molecular size increases, London forces also increases. And the strength of London forces also increases. I have a question. Boiling point of argon with atomic number 18 is 873 Kelvin, whereas the boiling point of neon with atomic number 10 is 27 Kelvin. Which of these have stronger London forces? As we have already seen, greater the atomic size, greater is the magnitude of London forces. So out of argon and neon, which is larger in size? Of course, argon is larger in size because it has a higher atomic size, sorry, a higher atomic number, and we know in the inert gas group, neon argon comes after neon down the group. So argon is having larger size than neon. Therefore, London forces are stronger in argon. The second factor which affects the London forces is molecular weight of the substance. As the atomic weight of the atom or the molecular weight of the molecule increases, atomic size also increases. The surface area of the substance also increases, and therefore London forces will be stronger. So in short, as the molecular weight of the substance increases, London forces also becomes stronger. Now let's compare the boiling point of two alkenes, octane and hexane. Octane, as you know, is an alkane with 8 carbon atoms, and hexane is a molecule with 6 carbon atoms. So obviously, the molecular weight of octane will be larger. The formula of octane is C8H18. The formula of hexane is C6H14. So obviously, octane is having higher molecular weight, which means London forces are stronger in octane, and therefore boiling point will also be higher for octane. The third factor which affects magnitude of London forces is the molecular shape. Some molecules have such a shape which provides maximum chances of attraction between them. Such molecules will have higher boiling point. One example is normal pentane. The formula of normal pentane is C5H12. Let's compare it with neopentane. Neopentane and normal pentane are isomers. Both have same molecular formula C5H12. But the structure of normal pentane is such that it has a zigzag shape, and therefore it can be, different normal pentane molecules can be arranged closely together, and therefore the attraction between them will be higher. Whereas in the case of neopentane, because of its structure, such kind of close packed arrangement is not possible. Therefore, neopentane has a higher boiling point of 309.1 Kelvin compared to that of neopentane, that is 282.5 Kelvin. So, normal pentane, in which close interaction between molecules is possible, has a higher boiling point than neopentane, another isomer of normal pentane, which has lesser boiling point because of the less interaction between the different molecules. There's pressure. At high pressure, atoms or molecules come close to each other. Therefore, the interactions between them will be higher, and the magnitude of London forces therefore increases with increase in pressure. The last factor which affects the magnitude of London forces is the number of electrons in atoms. As we know, atoms and molecules having larger size obviously will have large number of electrons. Means the electron clouds will be large. So this will result in greater diffusion of electron clouds and in turn greater polarization, which means there will be stronger interatomic or intermolecular interactions. Therefore, atoms and molecules with large number of electrons have large boiling point. So these are the different factors which affect the magnitude of van der Waals forces. Now that you have understood the significance of van der Waals forces, let's see the consequences of van der Waals forces. The physical state of a substance depends upon the magnitude of van der Waals forces. If you take the example of halogen family, as we move down the group, we know the size of the atoms increases. Also, the number of electrons in it also increases. So this will lead to an increase in the magnitude of van der Waals forces. And when the magnitude of van der Waals forces increases, the boiling point also increases. So as we move down the group in the halogen family, the boiling point increases. That is why at normal temperature, fluorine and chlorine exist as gases, whereas bromine is a liquid and iodine is a solid. Another effect of van der Waals forces is on the melting point and boiling point of a substance. Van der Waals forces brings the molecules closer, and when a substance undergoes melting or boiling, it involves absorption of heat to overcome the molecular attractions and to pull the molecules apart. So when you heat a substance, it will undergo melting or boiling point. Now this happens by absorbing heat, and what happens when the substance absorbs heat? That the heat absorbed is utilized to overcome the molecular attractions, and this will lead to separation of the molecules. So with increase in magnitude of van der Waals forces, the melting point and boiling point of substance increases. If you look at the noble gas family, the boiling point of noble gases increases from helium to radon down the group. This is because as we move down the group, the size of atom increases, also the number of electrons also increases, which will lead to an increase in the magnitude of van der Waals forces. Therefore, the boiling point of these atoms also increases. Another effect is on the liquefaction of gases. Means a gas can be liquefied because of the presence of this van der Waals forces. Liquefaction of gases occurs due to increase in intermolecular forces. When we cool a gas to a low temperature, or if you subject it to high pressure, what happens? The molecules, the gas molecules come closer to each other, leading to an increase in van der Waals forces. And when the molecules come closer, the gas will get liquefied. The gas will be converted to a liquid. So this is the process of liquefaction, and that occurs due to van der Waals forces. Now we have studied in your lower classes that real gases deviate from ideal behavior. These gases, or real gases, deviate from ideal behavior at conditions of low temperature and high pressure. This occurs due to the existence of van der Waals forces. So the deviation of real gases from ideal behavior also occurs due to the presence of van der Waals forces between the molecules. Now next effect is on the hardness of solids. The hardness of solids depends on the attractive forces between the constituent units. If the solid is made up of atoms or ions, the attractive forces between these atoms or ions leads to hardness of solids. So stronger the attractive forces, harder will be the solid. Let's compare two solids. One is diamond and the other is dry ice. I hope you know what in by dry ice. Dry ice is solid carbon dioxide. We know diamond is a hard solid, whereas dry ice is a soft solid. Means the hardness of these two solids differs. Now why is diamond a hard solid? Because in diamond, the atoms in diamond are held together by strong covalent bonds, whereas in dry ice, the atoms are held together by weak van der Waals forces. So these are some of the consequences of van der Waals.